Now we're looking at the unrestricted growth and decay models, and that's going to come in this formula, unrestricted growth and decay. So let's talk about what these things represent. A as a function of t, that means the amount that I have as a function of time is equal to the amount that I started with, a sub 0, times the number e raised to the k times t. Notice this isn't an r anymore. It looks kind of like PERT, but instead of principal, we say initial amount, and instead of rate, we say our constant growth. It's the same function, we just use different letters because of the different conversation that we're having. T is still time. Now the difference is if I have growth, then k has to be a positive exponent. If we have decay, k has to be a negative exponent. Well, look at how this looks on our graph. Remember, if we had exponential functions, this was a growth function, this was a decay function. And when this had a positive exponent, this had a negative exponent or a fractional number raised to the positive exponent. So we have growth and we have decay. What they start with here at a sub 0 is, remember, negative time doesn't make a lot of sense if you're counting the number of cells of bacteria or something like that, because you don't know how much was there prior to the time you started. So in that particular context, we don't have a negative side to this. So we're only going to look at our initial value, what we had when we started, and the following results. So in this, they gave us a different equation and they used different letters, but it still means the same thing. We have the number of cells as a function of time. We have our initial number of cells, the number e, raised to the k times t. K is a positive constant for growth. And the time in this problem, notice, a colony of bacteria grows according to the law of uninhibited growth, according to this function, where n is measured in, and that's a typo, n is measured in cells, and t is measured in days, not in years for this problem. We are measured in days. So the first three questions are basically straightforward. What was the initial amount of bacteria? Well, we can find that right here in our equation, and we had 90 cells of our bacteria when we started. What is the growth rate? That can be found right here. Now, we don't write 0.05, we would write the growth rate is 5%. What is the population after 5 days? Well, that's going to be a time, so we're going to come over here, we're going to take our equation, and we're going to find the number of cells based on 5 days. And that's going to be 90 times e to the 0.05 times 5. You plug that in, you're going to get a decimal number, which is approximately 115.36. If you get a slightly different number, don't worry about it. I do know it may be 115.56. But I do know that if I have a part of a cell, since we're talking about an entire cell, over here I would say I would have 116 cells after 5 days. So those were just straightforward problems. No needs for logarithms or exponents for these problems. But what if I didn't give you all this information? I didn't give you the time. It says how long will it take to reach 140 cells? So the 140 cells is the number of cells as a function of time. So to solve question D, I'm going to write 140 cells. Oh, don't know why I wrote an equal sign there. 140 cells equals 90 times e to the 0.05 t. Now, we learned in our last section that we can't log roll this unless we have a base exponent by itself. So I'm going to divide by 90. 140 divided by 90 is the same as 14 over 9. And then, of course, 90 divided by 90 cancels. And we now have 14/9 equals e to the 0.05 t. At this point, I'm going to roll it. I'm going to use natural log because the base is e. So it's the natural log of 14/9 equals 0.05 times t. I'm going to divide by 0.05. So the natural log of 14/9 divided by 0.05 equals t. And it will take me approximately 8.84 days to have 140 cells, 8.84 days. How long will it take me to double? Well, now in this case, they told me my initial amount. So how much would there be if it was doubled? Doubled, I'd have 180 cells equals 90 times e to the 0.05 t. When I divide by 90, what's 180 divided by 90? There it is. There's our doubling. 2 equals e to the 0.05 t, because 180 divided by 90 is 2. To solve this, at this point, I'm going to roll it. The natural log of 2 equals 0.05 t. So the natural log of 2 divided by 0.05 will give me the time. So it's going to take me approximately 13.86 days to double the number of bacteria. Our next problem is a carbon dating problem. If you ever heard about carbon dating, that's where they find out how something old is based on how much carbon is actually available in the item. Now, once again, these things are formulaic. No one is actually alive when this tree was cut down, so it's not like we can ask them, but we're going to use a formula to figure it out. And the formula we're going to use is this one right here. That's the unrestricted growth or decay, and they've told me this is decay because the K value is going to be negative. We are looking for a rate of decay. And it says the traces of burned wood along the ancient stone tools in the archaeological dig showed 1.67% of the original. Now think about what we did when we wanted to double the original. We started with the original amount and we doubled it, right? We had double that amount. But what if this was all that I had left? All that I have is 0.0167 of the original amount. That's what I have left. The formula then is times e to the k t. Well, the a's cancel, and I've got 0.0167 equals e to the kt. Now, I have a problem here. I can't solve because there's two variables. It says how old, when was the tree cut and burned? I don't know, because I don't know the K value. And the K value changes depending on what's called the half-life of the element you're working with. So let's make another equation. I had an initial amount of it. I know that it took me 5,600 years. And the constant, T is the time, K is the constant. I don't know that value, but I know that in 5,600 years, I will have half of what I started with. Now, they didn't have half, so we can't put a half there. But I would have half if I had 5,600 years to do it. The a to the 0 cancels, and so I've got 1/2 equals e to the 5,600k. To solve this, I'm going to do natural log of 1/2 equals 5,600k. So natural log of 1/2 divided by 5,600 is the constant value. And so when I'm looking at this problem, I'm going to enter the natural log of 1/2 divided by 5,600 years. Okay? And I get a value that looks very, very amazingly like negative 1.2377. This is not. Notice here at the end, e to the -4th means that that's actually, and I'm going to approximate it, I'm only going to put 4 decimal places, that's approximately negative 0.0001237, okay? Or 1238, sorry. When I look at that number, please be careful to notice whether there's this is scientific notation. This is negative 1.23776282 times 10 to the -4th. You have to be aware of that. But what am I going to do with that value? I can now plug that in to my equation. And now I have a number I can solve for. Now I'm just going to write it, round it off, as e to the -0.0001238 times t. But I'm going to actually use my calculator and the capture function instead of typing in that number. Oh, that's a t right there. Sorry, that got to be a mess. How do I solve? Well, the natural log of 0.0167 equals negative 0.000123 t, and the natural log of 0.0167 divided by negative 0.000123 is equal to t. Now, ladies and gentlemen, if you don't want to write that number over and over, you're welcome to put the letter k, but know what it's worth. So now I'm going to do the natural log of 0.0167 divided by, and notice I'm going to up arrow. Can you see how it highlighted that history problem right there? Enter, and it's going to say the natural log of this divided by my number. And this piece of wood, the tree that was cut and burned, was burned, according to this formula, approximately 33,062 years ago. So I would say that the time that this tree was cut and burned was approximately 33,000 years ago. Okay, and that's an approximate because we know our t value was actually 33,062 point something. So we're going to say about 33,000 years ago. This last problem uses our last formula from the sheet, and the last formula on the sheet was Newton's law of cooling. There's a lot of variables in here, so let's talk about it for a minute. The U in this particular problem is related to the temperature of the current temperature based on the amount of time that your object has been cooling. So this is the temperature as a result of time equals, the capital T stands for what we call the ambient temperature, or the temperature of the air in the room. Some people call it room temperature. It could be, if the room is the refrigerator, it'd be refrigerator temperature. If it's freezing in Wisconsin, this temperature would be the outside temperature if you had the cake outside. So that's the ambient temperature. The initial temperature of your object, once again, minus the ambient temperature, times E to the KT, and K is a constant. This is cooling. This is a decay problem. So our K value here is negative. So let's look at this word problem. And it says that we had a cake, we heated it to 350 degrees, and then we took it out of the oven. So in other words, this is our U sub 0. That's our initial time. We allowed it to cool in a room whose air temperature, or ambient temperature, was 70 degrees. That's my capital T. Then it says the temperature of the cake was 300 after 5 minutes. This is my U sub T if T equals 5 minutes. So I have U sub 0, I have U sub T, I have lowercase t, and capital T. What I'm missing is the K, and I can't find out when it will be 200 degrees until I have the K value. So I'm going to set up a problem for part A. The very first part I'm going to set up is that I have an 300 degree temperature at 5 minutes. So U sub T is 300 equals 70 degree ambient temperature, there's my capital T, plus my initial temperature minus the ambient temperature times E to the K times 5, because we knew it was 5 minutes. Solving this problem, I'm going to subtract 70, so 230 equals, I'm going to subtract 70, 280 times E to the 5K. I hope you're okay with me switching those around. I always get uncomfortable when I multiply the K first. Now I'm going to divide. 230 divided by 280 is 23 over 28 equals E to the 5K. We're going to roll it using natural log. So the natural log of 23/28 equals 5K. K is equal to the natural log of 23/28 divided by 5. And when I type that into my calculator, the natural log of 23/28 divided by 5, I get a negative number. And that's good because remember, our K value was supposed to be negative so that we can have decay. Now, this does not have an E on the end, so we know this is actually the value. And I really only need you to write down 4 decimal places. So I'm going to put negative 0.0393. You're going to use the capture, but I'm going to say that K is equal to negative 0.0393. Now I can actually solve, this was all the pre-work. Now I can solve part A. And part A said, when will it equal 200? In other words, at what time, U sub t, will it equal 200? So 200 equals 70 for the ambient plus 350 initial minus 70 ambient times e to the negative 0.0393 times t, because we don't know how long it's going to take. We subtract 130 equals 280 e to the negative 0.0393 t. We're going to divide 13/28 equals e to the negative 0.0393 t. Take the natural log of both sides. We're going to roll it right here. Natural log of 13/28 equals negative 0.0393 t. And then finally, the natural log of 13/28 divided by negative 0.0393 will give me my t value. So I'm going to type this in, the natural log of 13/28 divided by, scroll up and capture, and it's going to take approximately 19 and a half minutes. 19 and a half minutes. And how do I know that it's minutes? Because it said the problem was minutes, 5 minutes, right? And so 19 and a half minutes to cool it to 200 degrees. Now, let's look at question B. It says determine the time, so once again we're looking for t, to reach 100. Well, to do this problem, we're going to solve problem B, we're going to set it equal to 100 degrees, but the same formula. 70 plus 350 minus 70 times e to the negative 0.0393 t. Work our way through. 30 equals 280 times e to the negative 0.0393 t. 3 divided by 28, when we simplify, we're going to divide, equals e to the negative 0.0393 t. Take the natural log of 3/28 equals negative 0.0393 t, and we divide. The natural log of 3/28 divided by negative 0.0393 will give me t. Now, when I enter this into the calculator this time, I'm going to say the natural log of 3/28 divided by, and I'm going to scroll all the way back up here until I get to the value I'm looking for. Now I'm going to capture that, and it will take me, oh, sorry, I typed it in wrong. Let me fix this. The natural log of 3 divided by 28, I had typed in 2, divided by, go up and capture, I knew the answer was wrong, 56.8 minutes. So it's going to take almost an hour. The time is going to be 56.8 minutes to get it to 100 degrees. The last question says, what do we notice about the temperature? Well, in 5 minutes it got to 300. To get to 200 it took 19.5 minutes, and to get to 100 it took 56.8 minutes. That was not linear. It is cooling. It is cooling less slowly. It's cooling less over time, right? It's going to take more time to cool, and it will never cool below 70 degrees. This cake will never cool below 70 degrees. So why is that? Let's look at our equation again. Our equation is 70 plus, meaning we have all of this exponential stuff shifted up 70. Our horizontal asymptote is at 70. The cake is never going to cool below whatever the t value is, because that is our horizontal asymptote. That's the end of exponential growth and decay. Good luck with section 5.7 and 5.8.